Welcome. Today we will be covering the second portion of the carboxylic acids chapter. So before we go through the reactions of the different carboxylic acids, we're first going to look at the reactivity of the different carbonyl groups. Each carbonyl group has slightly different reactivity based on the substituent attached. And this reactivity is determined by a combination of factors including induction, resonance, sterics, and the quality of the leaving group. We're looking at the most electrophilic carbonyl carbon as an acid chloride, and the least reactive carbonyl carbon in the amide bond. Acid chlorides are the most reactive derivative for two reasons. The first is induction. The chlorine is more electronegative than the carbon, and through the sigma bonding framework pulls electron density towards it, making the carbon more partial positive. And then the second reason is through resonance. The chlorine atom has a resonance structure where it can push its electron density towards the positive charge that can form on the carbonyl carbon, stabilizing it. However, this resonance contributor is an extremely minor contributor. Amides are the least reactive of the acid derivatives. This is because of two factors as well, induction and resonance. For induction, the nitrogen atom is less electronegative than either chlorine or oxygen, so there's less of an inductive effect. And we have a significant resonance contributor from the nitrogen where the lone pair is donated in to the carbocation. Aldehydes and ketones are also electrophilic at the carbonyl carbon, but the major difference between the reactivity of the carboxylic acid derivatives and aldehydes and ketones is the ability for this group to act as a leaving group. And so the reactions that we're going to go through today are nucleophilic acyl substitution reactions, where we have a nucleophile forming a new carbon nucleophile bond and the leaving group leaving. And so we're going to be undergoing this general mechanism for all of these reactions. A nucleophile attacks the carbonyl compound, forming a tetrahedral intermediate, and then the carbonyl reforms through the loss of a leaving group. Generally, hydrogen and carbon anions cannot be expelled as leaving groups, and that's why we need these other carboxylic acid-derived compounds to be able to do this mechanism. Here's a specific example of a reactivity of a carboxylic acid derivative. We can have a methoxy anion attack the acyl chloride, creating this tetrahedral intermediate. The chloride is going to be the best leaving group, so the oxygen electrons push down, ejecting the chlorine as a leaving group, forming the ester product. This is a little bit different than an SN2 mechanism because it's not concerted. We're going through that tetrahedral intermediate instead of breaking a bond and making a bond at the same time. Sometimes in order to facilitate this entire process, we will need to use a proton transfer, and we should keep in mind the conditions that the reactions run in when we go to draw this mechanism out. Under acidic conditions, we're rarely going to form a negative charge, and under basic conditions, we're rarely going to form a positive charge. So based on whichever conditions we use, we should have consistent charges and intermediates. In this reaction, we have a reaction in acidic conditions. So the first step will not be nucleophilic attack because that would form a negative charge. Instead, for our first step, we're going to have a protonation step occur on the carbonyl carbon. So under acidic conditions, this protonation step will always be the first step in the acyl substitution mechanism. After the protonation step occurs, the next step will be nucleophilic attack. So in this case, we have water undergoing nucleophilic attack at the carbonyl. This forms a tetrahedral intermediate. Then a proton transfer can occur. Under basic conditions, the carbonyl is not going to be protonated first, but instead the nucleophilic attack will occur first, and that will form an oxygen with a negative charge on it. And this would be consistent with having basic conditions. When we have an amine as a nucleophile, it will attack the carbonyl first without the carbonyl being protonated, and will have a tetrahedral intermediate that's a Zwitter ion, or an intermediate with both a positive and negative charge. So in general, we'll have this reaction sequence. Under acidic conditions, we'll have up to 3 proton transfers necessary. Proton transfer, then nucleophilic attack, then proton transfer, loss of leaving group, followed by proton transfer. So depending on the mechanism conditions that we use, we'll have to decide where the proton transfers occur in the mechanism. So let's take a look at this following reaction. We have an acid chloride reacting with water to form a carboxylic acid and HCl as a byproduct. In this case, the conditions are not acidic, so the carbonyl will not be protonated at first. Our first step will be nucleophilic attack, then the oxygen collapsing to eject the leaving group, and our last step will be a proton transfer to yield the carboxylic acid product. Because we're not in acidic conditions, the leaving group will not require, and also the leaving group will not require a protonation to leave. There is a proton transfer at the end, but the leaving group is able to leave as just chloride minus because that is a good leaving group. So for the reaction of acid halides, we'll undergo this typical pattern. We don't have a proton transfer necessary in the first step, nor in the step before the loss of the leaving group. So this reaction mechanism will be a bit simplified with just a nucleophilic attack, a loss of the leaving group, followed by a proton transfer. We can make acid chlorides from carboxylic acids using SOCl2. This mechanism is a little bit more complicated. The first aspect of the mechanism is to actually generate a good leaving group. So to begin with, we have the pi electrons of the carbonylic compound attacking the sulfur, creating this intermediate, which then the oxygen collapses, ejecting a chloride leaving group, and a proton transfer will occur to yield this intermediate. This intermediate is the key intermediate because now we've generated a good leaving group on the oxygen. After this occurs, we're going back to the original pattern that we discussed for this reaction, where we have a nucleophilic attack occur. Now we've got a better leaving group than chloride with this because it can eject as SO2 gas and a chloride ion. So we have reformation of the carbonyl and then formation of SO2 and the chloride ion. In the presence of water, an acid chloride will convert to a carboxylic acid. And this mechanism is as follows. We have water undergoing nucleophilic attack, then collapse of the tetrahedral intermediate to reform the carbonyl, and finally a proton transfer to liberate the carboxylic acid. Since we have a byproduct of hydrochloric acid in this process, we can often use pyridine as an additive to neutralize the HCl as it's formed. We can also take a carboxylic acid derivative acyl chloride. This is the most reactive of the carboxylic acids, so more or less it's going to react with most all of these reagents to form esters, anhydrides, carboxylic acids, or amides. In this case, we can react the acid chloride with an alcohol to form an ester. We'll have a slight difference based on the substitution of the alcohol. So if we have a more sterically hindered alcohol versus a less sterically hindered alcohol, like a secondary alcohol versus a primary alcohol, the primary alcohol will react much more quickly because it's sterically accessible, and so we'll have selectivity, regioselectivity, to form the primary ester instead of forming the ester on the secondary alcohol. We can also use acid chlorides to synthesize amides. In this case, we can use just ammonia to form an amide. We can use a primary amine to form a primary amide, an N substituted just once, and we can use a secondary amine to form a disubstituted amide. Since we don't have pyridine in these reactions to soak up the HCl that's produced as a byproduct, we're actually going to need 2 equivalents of the amine in these reactions because the first equivalent will be reacting with the HCl and it will be unable to be used for the reaction. We can also reduce an acid chloride to the alcohol using LAH, and this is the same reduction mechanism that we saw for ketones and for aldehydes. The first step is the hydride attacks the carbonyl compound at tetrahedral intermediate forms, which ejects the chlorine, and then we have a second molecule of LAH doing a second nucleophilic attack and reduction. Our last step will be a proton transfer. If we use lithium tri-tert-butoxy aluminum hydride instead of LAH, we'll be able to stop this reaction at the aldehyde stage. And this is because the reagent is more selective and it will react with acid chlorides much more quickly than anhydrides, and that's due to the steric bulk on the reagent. Remember, an acid chloride is the most reactive of our carbonyl compounds, so the bulky reagent will react quickly or more quickly with the more active electrophile than it will with an aldehyde. We can also react acid chlorides with a Grignard reagent to form a tertiary alcohol. In this case, we'll be forming two new carbon-carbon bonds and go from a carbonyl on an acid chloride to a tertiary carbon. And we'll be undergoing the same mechanism as reduction using LAH, where the Grignard reagent will attack, we'll expel chlorine as our leaving group, then we will have a second nucleophilic attack followed by a proton transfer. We have another organometallic reagent that we can use, and this reagent will act similarly to the Grignard reagent. This is the lithium dialkyl cuprate. And so this Gilman reagent is going to add only once to an acid chloride to form a ketone, as opposed to a Grignard reagent, which remember we had do two nucleophilic attacks to form a tertiary alcohol. So from here we can go from an acid chloride to a ketone. To summarize the reactions of acid chlorides, depending on the reagent and conditions that we use, there are many different molecules that we can convert the acid chlorides to. The acid chlorides are great intermediates because of the versatility of the different products that we can acquire using them. And for synthesis reaction, if you need to form any of these molecules, you can first prepare the acid chloride from the carboxylic acid and then convert that to any of these ketones or carboxylic acid derivatives. Now we will swap pace and look at acid anhydrides. We can synthesize an anhydride by excessively heating the carboxylic acid. So if we have a carboxylic acid heated at 800 degrees Celsius, we will form the acetic anhydride. But this only works for acetic acid. Most acids won't be able to survive temperatures at 800 degrees. So we have a few other syntheses that we can use. Guess what? Acid chloride can be employed again. This time our nucleophile will be an acetate anion. And so our mechanism, we have nucleophilic attack of the acetate anion at the acid chloride, open up the tetrahedral intermediate, which then can close back down, expelling chlorine as a leaving group, and the anhydride is formed. These are both relatively good leaving groups, so we're going to have fairly good reactivity on the anhydride, just like the acid chloride. In these cases, we don't need to use pyridine with anhydrides because the reaction mechanism is going to involve the formation of the acetate anion as a leaving group, and that can be used to soak up the strong acid that's formed in the reaction mechanism. So we won't go through all of the reactions that an acid chloride or an anhydride can undergo because they're analogous to the reactions of an acid chloride. We can take an anhydride and convert it to all of these same products as well as reduce it. We can use acid anhydrides to make acetylate and an amine or an alcohol into an ester and an amide. And this conversion will take the alcohol to the ester and the amine to the amide. The synthesis of aspirin on a commercial and Tylenol on a commercial levels use acetic anhydride as a common reagent to form these acetyl and amide groups. We can form esters by using an SN2 reaction with a carboxylate anion and an alkyl halide. In the first step, we use sodium hydroxide to deprotonate the carboxylic acid, and then we'll have an SN2 attack of the negative charge on the oxygen with methyl iodide to form the ester. We also have another reaction called the Fischer esterification, where in the presence of sulfuric acid, most commonly, and an alcohol, the carboxylic acid is in equilibrium with its ester analog. And the mechanism of this reaction is consistent with the mechanism of nucleophilic attack under acidic conditions. First, a proton transfer occurs, protonating the carbonyl group, and then we can have nucleophilic attack of the methanol to form our tetrahedral intermediate. Another proton transfer will occur that makes the hydroxyl group a good leaving group. And then finally we have our loss of a leaving group and reformation of the carbonyl as the water is expelled as a leaving group. Finally, one proton transfer to deprotonate the carbonyl will result in the ester as the product. This mechanism can be supported through an isotopic label experiment where we take an oxygen and convert it to oxygen 18, and the oxygen on the methanol will show up as the oxygen attached to the methyl group in the ester product. All of the steps in this mechanism are equilibrium processes, and most of them are proton transfer processes. So this means that we can push the equilibrium by adding extra water to one side of the reaction and convert it back to the carboxylic acid. If we want to form the methyl ester, then we want to add excess methanol, and it's also helpful to remove the water as the reaction proceeds. We can also prepare an ester through the treatment of acid chloride with an alcohol. This mechanism was shown earlier in the PowerPoint. Esters can undergo hydrolysis under basic conditions. We can convert an ester back to the alcohol using sodium hydroxide and with an acidic workup. And acidic workup is necessary to obtain the neutral carboxylic acid pattern. The mechanism for this reaction will be consistent with the mechanism for nucleophilic attack under basic conditions. Our first step will be nucleophilic attack, followed by collapse of the carbonyl and ejection of the leaving group, and then a proton transfer to form the acetate anion. Under acidic conditions, we can reverse the equilibrium of the Fischer esterification, and to do this we would need excess water. In this case we have, and this mechanism is more or less going to be the exact opposite mechanism that we saw for the Fischer esterification. We're converting an ester to its carboxylic acid. We begin with protonation of the carbonyl carbon, followed by nucleophilic attack with water, which creates our tetrahedral intermediate that can then be deprotonated to form the alcohol. A second proton transfer creates this methoxy group as a good leaving group, and collapse of the oxygen lone pair to reform the carbonyl will then eject our good leaving group, forming carboxylic acid after one additional proton transfer. So this mechanism itself has 4 proton transfer steps. We can undergo a similar reaction with ammonia to form an amide from an ester. The overall equilibrium favors the amide formation because amides are more stable than esters. However, this is quite a slow process, and in most cases we're going to want to, instead of using an ester, convert an acid chloride to these different carboxylic acid derivatives. We can also undergo reduction of esters using LAH. We'll need at least 2 equivalents of the reducing agent for this, and form 2 equivalents of the alcohol product because we are reducing 2 carbon-oxygen bonds. And this mechanism will be exactly the same as the mechanism that we looked at for the acid halide. First we have the hydride attack, followed by collapse of the carbonyl and ejection of the leaving group, and then a second nucleophilic attack followed by a proton transfer. We can reduce an ester down to an aldehyde by using a specialized aluminum reagent called Dibol. This will reduce at low temperature only to the aldehyde, and we can selectively obtain the aldehyde from the ester. We can also react an ester with the Grignard reagent. This will form a tertiary alcohol, so it will react with two equivalents of the Grignard reagent. The reaction end mechanism is also analogous to the reaction of an acid halide with the Grignard reagent, where we have the same series of steps in the mechanism. Because an amide is the least reactive and most stable, we're able to synthesize amides from any of the carboxylic acids that we already discussed. Converting an acid chloride into any of these other carboxylic acid derivatives is going to be the most efficient. And with regards to an amide, it's important that we use two equivalents of the ammonia so that way we can neutralize the HCl byproduct that's formed from the reaction. We can also hydrolyze an amide with acid using heat and acid, but it's a slow reaction that requires high temperatures. The products for this reaction are favored at equilibrium because the ammonia group is protonated and not capable of acting like a nucleophile to reverse the reaction. So over time, we will be able to fully convert our amide into a carboxylic acid using these conditions. The mechanism is as follows. Since we're in acidic conditions, we begin with a proton transfer, followed by nucleophilic attack. Then we do another proton transfer to protonate the ammonia. And at this point we can have reformation of the carbonyl group as well as ejection of the leaving group, which is ammonia, to form the carboxylic acid, protonated carboxylic acid, which after one more proton transfer furnishes the acid product. Amides can also be hydrolyzed under basic conditions, so sodium hydroxide in heat. This will be even slower than acidic conditions, but the mechanism will be analogous to the hydrolysis of an ester, where first we have nucleophilic attack occur. Remember, in basic conditions, nucleophilic attack of the anion is always going to be the first step, which leads to an anion tetrahedral intermediate, which then can collapse and expel the leaving group, which can then undergo a deprotonation. This gives the negative carboxylate ion, which will form the product in an acidic workup. Amides can be reduced to the amine with LAH, and this mechanism will actually be a little bit different than what we've seen before. The carbonyl group is completely removed while the nitrogen remains bound to the molecule. The last series of reactions that we will look at is the preparation of nitriles. So if we have a primary or secondary alkyl halide that's treated with a cyanide ion, we can do an SN2 reaction to form the nitrile. And then this nitrile could also be formed by the dehydration of a primary amide using SOCl2. So we could convert the primary amide to the nitrile, and our byproducts are SO2 and HCl. This undergoes a mechanism similar to what we've seen in the acid chloride formation reaction, where we have nucleophilic attack of the sulfur and then collapse to form a good leaving group. A base will do a proton transfer to deprotonate this imine, which then can collapse down and eject out our good leaving group to form the nitrile product. And we've already shown this reaction before, but under acidic conditions we can convert an nitrile to an amide intermediate, and then the amide will further on convert to the carboxylic acid. Our mechanism here, we begin by protonation of the nitrogen lone pair, then nucleophilic attack of the oxygen on the carbon of the nitrile. So this carbon can act similar to a carbonyl carbon because of the carbon triple bond to the nitrogen. This forms an imine intermediate, which can then undergo a series of proton transfers, which lead us to the amide product. And this hydrolysis can also occur under basic conditions, but will have a slightly different mechanism. We'll begin by nucleophilic attack of the oxygen on the carbon, forming an imine intermediate. Then we can do a couple proton transfer events, which will eventually afford the amide product. We can also react nitriles with Grignard reagents, and they'll be reactive at this carbon, which we can think of as analogous to a carbonyl carbon. The R group of the Grignard would form a new carbon-carbon bond there, forming this nitrogen negative charge intermediate, which can then be protonated with an aqueous workup. And finally, similar to how carboxylic acids can be converted to alcohols using LAH, we can convert nitriles to primary amines using LAH as well.